part of the reading that describes the connection between these graphs. Now I want to go one step further with this and show you what a motion diagram would look like for this. And before I do that, I'm going to minimize these graphs. Okay, so in making a motion diagram, we're going to use dots to represent the location of the object. And let's say it starts right here. Now after 1 second, it's displaced a total of 2.5 meters. So let's make that little distance there represent 2.5 meters. And then after the next second, it's gone an additional 7.5, which is interestingly 3 times that far. And then an additional 12.5, which is interestingly 5 times as far as it had originally gone. And then again, that much additional displacement, followed by again another 7.5, and then another 2.5, and then it displaces 2.5 in the other direction. That would be right back on top of that dot. We wouldn't be able to see any details, so in our motion diagram we just drop down a line here, and then again another 7.5 in that direction. Alright, now with the motion diagrams, not only do we want to do dots to represent position, but we want to do arrows to represent velocity and acceleration. So to begin with, it's not moving at all, but it does have an acceleration. That acceleration causes it to speed up. And so that acceleration coupled with the initial velocity of 0 gives a new velocity, which if I was really good at drawing would have that arrow length be the same as that, because the acceleration represents how much the velocity has changed. Now at that instant in time there, we still have an acceleration of 5 meters per second, as do we have that same acceleration here. Now, this acceleration coupled with that gives us a new velocity that at least pictorially could get by adding that length and that length. That is, we get the new velocity by taking the old velocity and adding it to the acceleration. The acceleration represents how much the velocity has changed. Alright, now in the third second, then we're going that fast in a second plus that much change gives us a new velocity, which would be that length plus that length. But here's where the acceleration switches around. We've switched the direction of our rocket. That acceleration then persists for the remainder of the trip. Always putting the acceleration vectors below the dots. Now what does that mean for our velocity? Well, our new velocity will be our old velocity plus the change, so somewhat shorter, and then shorter still by that amount. And then no velocity here. If you want to put a little dot, you could do that, but you don't even need to. The arrow, the vector, is no length because it's at rest there. And then back again like this, because we take 0 velocity and add that much change to get the new velocity. The old velocity plus that much change to get the new velocity. So here's a motion diagram of the rocket car's motion. And I want to point out one interesting thing, which we could also see from the data table, is that at this point, notice there's no velocity, and yet there is acceleration. Okay, that occurs right here. There is acceleration, but no velocity. A lot of people get velocity and acceleration confused and think that, hey, if the object's not moving, it can't be accelerating. But acceleration just tells you how much the moving is changing. And so even if you're at rest, you could be changing, and you know you will be, because if the next instant you're not at rest, then you've changed your motion. The same thing happens here. It's not moving, but it is accelerating. And if that idea is difficult for you to think about, it's because for the most part, people use acceleration and velocity differently sometimes, but sometimes they use it to mean the same thing, motion. And so in this case, if you use acceleration to mean pretty much the same thing as velocity, you would say, yeah, hey, how can I have acceleration but not be moving? Well, again, they're different things. Acceleration doesn't tell you anything about the motion.